I've been exposed to such a rich tapestry of cultures.
It's so cool. Like, we enjoyed it so much the moment we stepped in here.
Ridge regression versus lasso regression. Which one will survive? StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about ridge versus lasso regression, and the differences are going to be visualized. Note, this StatQuest assumes that you are already familiar with ridge and lasso regression. If not, check out the quests. To show you the difference between ridge and lasso regression, we're going to use a very simple dataset that consists of weight and height measurements. And we'll start by fitting this horizontal line to the data. This horizontal line represents a terrible fit. And we can measure how bad that fit is by calculating residuals, the difference between the observed and predicted values. In order to compare the horizontal line to other lines fit to the data, we will plot the sum of the squared residuals on a graph. The y-axis on this graph is the sum of the squared residuals, and the x-axis represents different slope values for the fitted line. In this case, the slope for the horizontal line is 0. Now let's increase the slope to 0.2. and calculate a new value for the sum of the squared residuals. Now let's increase the slope to 0.4 and calculate a new value for the sum of the squared residuals. We can keep plugging in new values for the slope and plotting the sum of the squared residuals, or we can just plot the curve for this equation. We can see that the best fitting line is at the bottom of the parabola. In other words, when the slope equals 0.45, we get the lowest sum of the squared residuals. In this example, we simply calculated the sum of the squared residuals for different slopes. Now let's add the ridge regression penalty, aka the L2 norm. Note, if you asked me, it should be called the squared penalty, since that's what it is, and, for me, way easier to remember. The thick blue line that we just drew represents lambda equals 0. This is because when lambda equals 0, the penalty is equal to 0, regardless of the slope, and we are left with the original sum of squared residuals. Now let's see what happens when we set lambda equal to 10. And just like before, we'll start with a horizontal line, only this time the line is orange. Just like before, we can calculate the residuals. And we can calculate the sum of the squared residuals plus lambda times the slope squared. In this case, lambda equals 10. And the slope of the horizontal line is 0. So the penalty is 0. So we plot the sum of the squared residuals here. Now let's increase the slope to 0.2. Note, the residuals are smaller than before, so the sum of squared residuals is smaller than before. But now the penalty is 0.4. And that gives us this point on the graph. Now let's increase the slope to 0.4. And the residuals are even smaller. But now the penalty is 1.6. And that gives us this point on the graph. And like we did before, we can keep plugging in new values for the slope and plotting the sum of the squared residuals plus the penalty, or we can just plot the curve with a thick orange line that represents lambda equals 10. The bottom of the parabola is where the slope gives us the lowest sum of squared residuals plus penalty. And that corresponds to this specific line. And when we compare that to the optimal slope when lambda equals 0, we see that setting lambda equal to 10 results in a smaller optimal slope. Note, we can also see that when lambda equals 10, the lowest point in the parabola is closer to 0 than when lambda equals 0. So, either way we look at it, we see that the larger value for lambda shrunk the optimal value for the slope. Likewise, the thick green line represents lambda equals 20. We see that the minimum value is closer to 0, and the optimal slope has shrunk some more. The purple lines represent lambda equals 40, and it shrinks the slope even more. In other words, as we increase lambda for the ridge regression penalty, aka the L2 penalty, aka the square penalty, the optimal slope gets closer and closer to 0, but it does not equal 0. Bam! Now let's see what happens if we use the lasso penalty, aka the L1 norm, or, if you asked me, I'd call it the absolute value penalty. Unfortunately, no one asked me. Again, the thick blue line represents lambda equals 0, so there is no extra penalty. This is because when we plug lambda equals 0 into the equation, the penalty becomes 0.
This is a mechanical jacquard loom. This technology was developed in France in 1803 by a weaver named Joseph Marie Jacquard. France in 1803 by a weaver named Joseph Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually. Because it can do that, the loom can create very complex, fancy patterns in the cloth. That the loom involves every warp thread, the threads that go thing about her named Joseph Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually. Because it can do that, the loom can create very complex, fancy patterns in the cloth more quickly and with greater accuracy than the technology available before this loom was developed. These cards are what carry the instructions that are read by the apparatus on the second floor that tells the loom what pattern to create. The holes in the cards are read by a series of pins up in the apparatus, and those holes tell the apparatus which threads down here should be raised for each pass of my shuttle across the warp. Some of you might recognize these cards as looking similar to computer punch cards. Back in the early days of computer technology, punch cards carried instructions that told the early computers what kind of calculations to do. So this loom is the great-great-great-grandfather of the computer technology that we all use today, and that technology started with a machine that produces cloth.
A jacquard loom, Joseph Jacquard lived in France, and he developed this technology in 1801. So here we've got basically the same very heavy beam construction.
Hello and welcome to Paradise Mill here in Macclesfield. Today we're going to be looking at the jacquard mechanism and the binary system it uses to control the patterns that it weaves on a loom. With weaving there are two options. Either you can lift up a warp thread so the weft will pass underneath and the weft will not be seen, or you can leave the warp thread down and the weft will pass over the warp thread and the weft will be seen. There are only two options, and when there are only two options, that is known as a binary system. It is the same with today's modern computers. They speak a binary language. Millions upon millions of ones and zeros are the set of instructions by which they understand the tasks given to them. With this old 19th century jacquard mechanism, it doesn't understand ones and zeros, or ons and offs, but it does understand the binary system of a hole or no hole punched into these cards. And this is how we program the loom to automatically weave a pattern. How does the jacquard mechanism actually work? When a weaver presses down the treadle on the loom, it causes this iron cage called a griff to rise up. Inside the griff, there are rows of bars known as knives. A hook will either catch onto the knife and lift up a harness of warp threads, or a hook will not catch onto the knife and remain down and leave the warp threads down. What controls whether the hooks catch onto the knife and are lifted up, or don't catch onto the knife and remain down, are the punched cards. How does the Jacquard mechanism read these punch cards and understand them in order to lift up or leave down the warp threads? When the weaver presses down on the treadle, this four-sided cylinder will swing out and turn 90 degrees to select the next card in the pattern. One card is one pass of the shuttle. One line in the pattern, one weft thread, also known as a pick. The full set of cards are looped together in order, and this is the complete pattern. The punched cards sit in line with all the holes around the cylinder block. When the cylinder comes to rest against this bank of needles, the next pick selection is made. Some of the needles will be allowed into the cylinder if there's a hole punched into the card to let them through. If there is no hole punched into the card, it is going to push the needle back. And when the needle is pushed back, the hook gets pushed back. And it is not going to catch on the knife inside the griff when that rises up as the weaver presses down on the treadle. Each hook in the mechanism passes through a needle. All the needles are spring-loaded. When the cylinder swings out as the treadle is pressed down, they all return to the same position ready for the next card in the sequence and the next pick selection. In the binary language of the Jacquard mechanism, a hole is the instruction to lift up a harness of warp threads. No hole in the card tells the mechanism to leave the harness of warp threads down. How are the punched cards programmed? If I want to leave one particular hook down, I need to push in the needle that it goes through. If I push that needle in and I press down the treadle on the loom, I am going to lift up every single hook except for the one where I have pushed the needle in. Great accuracy is therefore needed in punching all the holes in the correct place so there are no errors in the woven pattern. Card sets can be programmed to produce different patterns or even pictures. A Jacquard designer has to produce a draft of the pattern on gridded paper called point paper, such as this picture of a weaver at a Jacquard loom. A card cutter then has to carefully read this draft and cut holes in the cards in the correct place and in the correct order as at a Jacquard loom. A card cutter then has to carefully read this draft and cut holes in the cards in the correct place and in the correct order as indicated by the colours in each segment. Before digital technology, early computer software was programmed in a similar way by punching holes in cards. If we zoom in close to the woven picture, we can see how it is made in each segment. Before digital technology, early computer software was programmed in a similar way by punching holes in cards. If we zoom in close to the woven picture, we can see how it is made up of the lighter colour weft threads passing over the black warp so they are visible. The image is made up of lots of tiny lines of visible weft. If you zoom all the way into a digital image, you will see it is made up of lots of tiny blocks called pixels. The Jacquard loom with its punched cards is a programmable machine. The Jacquard mechanism is the ancestor of modern digital technology today. The common language of both is binary.
وضع خيط اللحمة في النفس في ماكينات النسيج. يعتبر وضع خيط اللحمة في النفس هو قلب مراحل النسيج، هي الأساس. كان في البداية بعد الثورة الصناعية
مشاهدينا الكرام، بعد ما بيوصل القطن هنا في مصانع الغزل والنسيج بمنطقة الروبيكي بيمر بمراحل النسيج الاستخدام العام. كل مراحل
السلام عليكم ورحمة الله تعالى وبركاته. مرحبا بكم معايا في هذا الفيديو جديد. إن شاء الله تكونوا بخير. هذا الفيديو يلقاكم بخير. وكيفاش هكذا 4 ونديروا هذه سموها السيركلو سطرين هكذا.
مرحبا يا عشاق الذكاء الاصطناعي الأعزاء.
At Princeton University lives New Jersey's most famous foreign-born citizen, Professor Albert Einstein, who helped discover the atom bomb.
السلام عليكم، ازيكم يا حبايبي؟ عاملين ايه؟ يا رب تكونوا بخير.
Charles Babbage was the only child of a tyrannical London banker, a bully at home, but his money
Organizations today
Charles Babbage was the only child of a tyrannical London banker, a bully at home, but his money kept his son and heir financially comfortable for life. Cambridge educated in mathematics and supremely self-possessed, Charles became an iconoclastic writer and habitual inventor. In 1832, the drawing room of his London home became a showcase for demonstrations of a small section of his difference engine, a far from finished device by which he intended to revolutionize calculation by mechanizing it. At his soirees, London's intellectual society watched what you see now, as Babbage cranked its handle. This machine produced a series of polynomial calculations that were repeatable and error-free. Most astonishing, it was automatic. Any of his illustrious guests might have operated the handle as well as Charles Babbage, perhaps the geologist Charles Lyell, or Charles Darwin, or Charles Dickens. Once set, the machine seemed able to proceed, to think on its own. But what was called the beautiful fragment of the machine Babbage had intended to build was all he ever finished of it. In fact, his imagination had already moved on to an even more ambitious mechanism. One that would make obsolete the abandoned machine. The analytical engine would be a general-purpose calculating automaton. For most of 30 years, he would revise and improve his notional design. Only a few partial sections of it were built, this one after Babbage's death, by his son. The analytical engine was an ever-evolving machine. Each breakthrough elegantly drawn up, annotated to describe mechanical motions with a coding system that Babbage claimed was his finest invention. The analytical engine may be the most intricate operating mechanism ever fully realized with paper and imagination. Most intricate operating mechanism. The analytical engine may be the most intricate operating mechanism ever fully realized with paper and imagination alone. In 1846, Babbage abruptly changed course. As if determined to make good on an old obligation, he worked for 2 years to complete a full set of drawings for difference engine number 2. It would require 8,000 parts, only a third as many as the first. He offered it to the government, but did not protest when it declined to build it, and the drawings were carefully put away. Eventually, they came from the Babbage estate to rest in the library of the Science Museum in London. More than 130 years later, in 1985, the museum's new curator of computing, Doran Swade, became convinced the institution could build difference engine number 2. After all, with the intact drawings, it seemed feasible and within financial reach. It took 17 years and drama to rival Babbage's so long ago. And it works, just as Babbage designed it. Every turn of the engine's driving handle is carried through gears, cams, rods, levers, and springs to release and arrest precisely aligned number wheels. A helical arrangement of steel fingers continually pulls the register towers to find and perform the carrying of tens. In its continuing sweep upward, it is mesmerizing. The intricate printing section can be programmed for 1, 2, or 3 column output. for 2 font sizes at once, for variable margins and column gaps, even word wrap where necessary. It prints hard copy on paper and simultaneously impresses the same output into a tray of plaster to produce a stereotype, a mold for casting a full-page printing plate. When a tray is full, the printer pauses the entire machine. In the spring of 2008, a clone of DE2 commissioned by Nathan Myhrvold was completed at the Science Museum and shipped to California. At the Computer History Museum, it would charm new thousands of discerning eyes. Today, the crotchety proud genius, who never managed to prove it during his lifetime, has a fair claim to honor as a pioneer in the history of intelligent machines, just as his parlor guests in 1832 suggested. His difference engine continues to inspire the admiration of his intellectual heirs, a celebrated and unique icon to chroniclers of computing. Charles Babbage, remember, never saw it, except in his stubborn, prescient dreams.
Oxford Royale Academy offers you an authentic taste of the environment at a top institution. You live and learn in college. You are taught by outstanding academics passionate about their subjects, not to mention guest speakers of international repute. And enjoyment is always an important part of our award-winning program. Attending our courses will enable you to grasp your future with
Well, welcome. My name is Alan. You can say. My name is Alan. I'm a volunteer docent here at the Computer History Museum, and I'm going to tell you the story of the man, Charles Babbage, his machine designs, and how this amazing machine behind me happened to get built and come to our museum. Julie, standing down here by her crank, is the power supply of this machine, and it takes a lot of skill. She's very skilled at managing the various load on this crank, and she has to crank very steadily because there's a lot of stuff going on. And you'll be fascinated, I think, with the story of Babbage and his times, because you probably all know what it is to come to sort of develop something a little ahead of its time. So this is a story very, very familiar to some of us. So before I even begin talking about it, it's good to study it as a moving sculpture. So let's let Julie crank it through about 5 cycles here, and you guys can look at it. If you have we'll only have about 45 seconds, but you should kind of rotate around and go look at the back happening and come back here in front of me in a few seconds, and we'll talk about it. So let's just make it move. I'll get out of the way. down to the front. We'll talk a little bit here. Now, in that little brief time, Julie was solving an equation, what we call a fifth-order polynomial. She did it 5 times in that amount of time while we were watching the machine. And this machine is based on a mathematical principle called finite differences. And we're going to talk about that a little later. But first, let me back up to talk about the inventor. Charles Babbage was born in England in 1791. Son of a London banker. He was sent to university, very well educated in math. But first, let me back up to talk about the inventor. Charles Babbage was born in England in 1791, son of a London banker. He was sent to university, very well educated in mathematics and science. And if you look at the beginning of the 19th century, scientists were multidisciplined. That is, today we have this amazing specialization. But back then, scientists dabbled and mathematicians dabbled in a lot of different areas. And Babbage was one of those who we might call today a sort of Da Vinci man. He had lots of great ideas, and some of them got executed. And for example, he invented the ophthalmoscope that physicians look into your eyes with. That was complicated, but he also invented a simple thing called the cow catcher that goes on the front of locomotives. He also invented a semaphore signal to communicate between ships at sea and lighthouses. Very, very clever guy. On the other hand, like some residents of this valley, and I know, he wasn't great at communicating with other carbon-based life forms. He had a really kind of curmudgeon-y personality. I know. He wasn't great at communicating with other carbon-based life forms. He had a really kind of curmudgeon-y personality that got him in trouble, especially if you disagreed with him. And I think, it wasn't only in science and mathematics that happened. To give you an idea, an insight into his personality, I just want to read to you a letter he wrote to one of his contemporaries, the poet Tennyson, criticizing one of his poems and asking him to please change it. The letter reads, "Sir, in your otherwise beautiful poem, The Vision of Sin, there's a verse which reads, 'Every moment dies a man, every moment one is born.' It must be manifest that if this were true, the population of the world would be at a standstill. I would suggest," this is chutzpah, "I would suggest that the next edition of your poem you have it read, quote, 'Every moment dies a man, every moment, 1 1/16 is born.'" So that gives you a little clue into this sort of geeky personality here. Okay, the story of the machines really begins in the early 1820s when Babbage and a colleague have a project to review various publications of books of mathematical tables. Now, you all look almost old enough to remember the days when we had to use a slide rule in these books. Books to solve some of our problems, to look up natural logarithms or common logarithms, tables of integrals, trigonometric functions, and of course, Britain was the king of the seas, the world's superpower at the time, using astronomical tables to navigate on the ocean. Well, when he and his colleague looked at various publications of these books, what do you think they found? Yeah, one book was different than the next. Where is the error? That's the question. Babbage immediately said, we got to think of a way to recalculate these tables infallibly. After all, this is the Industrial Revolution. We're inventing railroads and factories, machinery of production. Surely we can figure out a way to do this. And he drew up a machine which today we call difference engine number 1. It relied on this principle of finite differences to solve up to 7th order polynomial equations. And he then, once he had it drawn up, he needed the next thing an entrepreneur needs to bring his device to reality, which is
This music was generated with the tool I'm showing you today.
Wait, what?
Money. There were no venture capitalists in England in the 1830s, so he went to the funder of last resort that everybody loves to get money from, the government, the crown. And they indeed said, okay, we will fund it. A very, very loosey-goosey contract, by the way. And Charles Babbage then needed the next ingredient, which was a very skilled machinist toolmaker. Because you have to remember, in those days, there were very few standards. How do you make gears reliably? There were no standards for screw threads, all that stuff. So he found a very good toolmaker who was, because he was a very good toolmaker, he was also a bit of a prima donna. So you can imagine these two guys communicating. First difference engine. The only thing that he ever built was a small demonstrator model, which is reproduced in a case over there if you get a chance to look at it. So he could demonstrate it at parties and when he was out trying to raise money for the project. So he moved on, though. He kept inventing things, and he went to work on a much more ambitious project. You think he would scale down. He scaled up. He drew up the analytical engine, which was a full-scale computer, mechanical computer, that could add, subtract, multiply, divide, branch, be programmed with punch cards. Yes, 1830s. It was an amazing machine. It would have been bigger than a locomotive. So I don't know how he ever thought anybody would build it, but it was a good mental exercise. Probably one of the largest mechanical devices ever envisioned by man. Next, while he was doing that, he thought he had a better idea for building the difference engine with fewer parts. And he designs difference engine number 2 in great detail. It has only a mere 8,000 parts. And he offers it to the British government, and they politely refuse. They say, we've moved on, Charlie. We already gave you enough money to build 20 locomotives, and you didn't produce anything. So that's the end of it. Charles Babbage, during his life, never built any of these machines. He said, another age, you'll have to judge whether any of them would have worked. Fast forward, 1985. 130 years later, roughly, the curator of the London Science Museum, Doran Swade, has Charles Babbage's drawings for difference engine number 2, and he says, I wonder if it will work. Let's try to build it. And they embark on a similar odyssey, money, time, machine shops, so that in 1991, Babbage's 200th birthday, they have the calculating set of the part of the machine built, from where Julie's standing through here, where you see 8 registers, 31-digit number registers, vertical registers of numbers, so that you can have 7 difference columns plus the result column. But the most important part of the machine, Babbage felt, was this part down here, which is the printer stereotyper. You see, anybody can do the math with finite differences and solve the equations, but how does one make sure that after that you don't make a mistake? Because if you write down the answer, people sometimes reverse digits. Then you give it to a printer who's using movable type, right? Very easy to mess that up. So he wanted to make sure that that didn't happen. This device takes the result from this register, transfers it to this printer here. You'll see the type wheels rotate. A little inker comes up, puts ink on the type. The paper is brought up to the printer and prints the answer. You won't see that actually print because we don't like to mess this thing up with the ink. It works like a printing press. Then, most importantly, this tray down here would be filled with a plastic material like plaster of Paris. Right after the print cycle, another set of type rotates down, impresses the answer into the plaster. The device, the tray is indexed in, waiting for the next answer, etc., till the page is full, the mold is full. A printer takes it, pours lead in there, has a printing plate, no movable type. So he did everything he possibly could to avoid error. And believe me, unless this machine is broken or jammed up, it cannot produce a wrong answer. So, now, as I said, by 1991, the museum had built this calculating section. How are they going to finish it? Their plight is seen by an American entrepreneur named Nathan Myhrvold. He was once the CTO of Microsoft. He's running a very interesting company up in Seattle now. I noticed they're just inventing a laser beam weapon that zaps mosquitoes that carry malaria. I'm not making that up, by the way.
It works. I've seen it.
You've seen it work? Okay, great. So anyway, he says, "I'll tell you what, London Science Museum, I'll fund you to finish this first serial number 1, but then I want you to build me a whole difference engine for my private collection." And this machine you see is Nathan Myhrvold's difference engine number 2, completed in March of 2008. And he's letting us keep it here to show it to you folks for a while, I hope, a long while, I hope. And afterwards, we're going to take it up and stick it in his living room. So, right next to the T-Rex skeleton, he's already got it there. So, okay. So let's now look again. Let's crank it. I want you to watch as the addition takes place. We've got this equation set up. So in fact, we're using 5 of the 7 difference columns. And you will see the addition taking place by these big sector gears in between, adding the numbers from one column by rotating them back.
One of my favorite ways to cut down on study time is to use AI tools. This is where Grammarly can help. Just open up Grammarly and ask it to help
towards 0 value, transferring their value to the next column, and then resetting the column to its original value as it comes down.